Hi, let us solve some more questions from the topic first law, and I'll take some questions from steady flow energy equation also in this video. Okay, so this one is from heat and work for open system, and this question can be solved using steady flow energy equation. Okay, so what we do is we take a control volume and then apply steady flow energy equation to all the data given. Let's see how it's done. So in a steady flow apparatus, 130 kilojoule of work is done by each kilogram of fluid. Okay, the specific volume of the fluid, pressure and velocity at the inlet is given. Okay, the inlet conditions are given to you. The inlet is 32 meters above the floor and the discharge pipe is at floor level. So you can take this floor level as datum. Okay, the discharge conditions are 0.62 meter cube per kg. This is specific volume, this is final pressure, and this is the velocity with which this fluid is discharged. The total heat loss between the inlet and discharge is 12 kilojoule of fluid. This is the heat loss. So be careful that you have to take it with a negative sign. Okay, sign conventions are very important, do not forget them. The change magnitude has been asked in specific internal energy, that is kilojoule per kilogram of the fluid in flowing through the apparatus is. Okay, so change in specific internal energy, that is delta U, U2 minus U1. Okay, so this you have to find its magnitude. Okay, so what is steady flow energy equation and how it is written? I'll tell you. SFEE. Okay, suppose this is the control volume here, and the inlet, this is the control volume, this dotted line. Let me draw it again. So the fluid is entering from some initial conditions, let them be I or let them be 1, whatever you want to denote, and the final conditions be, let them be 2. Okay, and this is the control volume, and you apply steady flow energy equation in this control volume. Okay, this is the control volume. So you apply steady flow energy equation within this control volume. Okay, by taking this as control volume. Okay, so steady flow energy equation is given by m dot h1 plus v1 square by 2 plus gz1 plus q dot is equal to, I'll explain you the terms, m dot h2 plus v2 square by 2 plus gz2 plus w dot. Okay, so this is the mass flow rate, this is the enthalpy of the fluid with which it is entering, and this is the velocity of the fluid that is entering, and this z is what? Z is actually the height. Okay, so in this case I'll be taking this floor level as datum, this floor level as datum, so this z becomes 0, and the inlet height becomes, what is given? This is given 32 meters, 32 meters, right? So the floor I have taken as datum, so this becomes 0, and this distance becomes 32. Okay, so respective distances of inlet and outlet from the datum are z1 and z2. S2 is the enthalpy of the outgoing fluid, and similarly v2 is the velocity of the outgoing fluid. Q dot, this is m dot mass flow rate, so here it will be q dot, that is rate of heat interaction taking place within this control volume. What is w dot? W dot is joule per second, that is power. Okay, power we'll be getting. If here it was given only mass instead of mass flow rate, then the equation becomes m, this whole equation, plus q, that is, now it will not be rate of heat transfer, it will be only heat interaction taking place, is equal to m, this equation, plus w. Now this will be work done, not power developed. Okay, and if there is, I mean, you have to find the terms in kilojoule per kilogram, like there is no information given about m, or there's given that mass is 1 kg, or basically it would be given that you have to find the terms in kilojoule per kilogram. So that means if there is no m term in this equation, the equation will be h1 plus v1 square by 2 plus gz1 plus small q, okay, that is heat interaction taking place per unit kg, okay, is equal to h2 plus v2 square by 2 plus gz2 plus, this is small q, okay, plus w, that is small w, that is again work done per unit kg of the mass. Okay, so this is how you write steady flow energy equation in 3 forms. This is basically a game of units, and that's why I always tell you to carefully see the units and carefully put the data in this equation. Okay, so I guess in this question everything is given to you. You have to find specific internal energy. Okay, so here the term is enthalpy, there is no internal energy term directly written, okay, directly. But what about this H? This H is basically U plus PV. Okay, enthalpy is U plus PV. So H1 becomes U1 P1 V1. This is specific volume. Okay, and H2 becomes U2 plus P2 V2. So now I think everything is given to you, and you can find U2 minus U1, and you can put the answer in, you have to find the magnitude of U2 minus U1 and put the answer in kilojoule per kilogram. Okay, so let's see the data. Okay, I'll see the data from here. So the pressure is 600 kilopascal initial pressure. So P1 is always put the values in SI units. Why? Because sometimes H1 will be given, I mean sometimes no, it will always be given in kilojoule per kilogram, but velocity will be in meter per second. So if you put H1 in kilojoule per kilogram and velocity in meter per second, you'll get the wrong answer. So you have to put H in joule per kilogram only. Okay, put in SI units, put all the data in SI units. Let me write it here for you. It's an important information. Try to put everything in SI units. Try to put every data in SI units. Okay, in SI units. Yeah. Okay. So this is. So we were putting the data. So P1 is 600 kilopascal. That is 600 into 10 raised to the power 3 pascal, and specific volume is given. That is 0.37 meter cube per kg. Next is this you have to find, I mean U2 minus U1 you have to find. V1 is what? V1 is given, which is 16 meter per second, and Z1 is 32 meters, Z2 is 0, and V2 is given to you. V2 is 270 meter per second, and P2 is what? P2 is 100 kilopascal, that is 100 into 10 to the power 3, and specific volume of the outgoing fluid, that is discharge, is 0.62 meter cube per kg. Okay, so every data is given to you. And what about Q and W? It's given that 130 kilojoule of work is done by each each kilogram of fluid. So work is done by the fluid, that means this is 130 with a positive sign, 130 kilojoule, right? Yes, so 130 into 10 raised to power 3. Okay, and some term is given, some data is given regarding heat transfer, which was the total heat loss between the inlet and discharge is 12 kilojoule per kilogram. Okay, so this is what, this is 130 kilojoule of work is done, yeah, by each kilo fluid, by each kilogram of fluid. So yeah, this was correct. So this is also 12 kilojoule per kilogram, and this is heat loss. Okay, so that implies it will be a it will be with a minus sign, so minus 12 kilojoule per kilogram. Okay, this is also kilojoule per kilogram. It's given that 130 kilojoule of work is done by each kilogram of fluid. Okay, so yeah, so this is also correct. Sometimes it's also given that sometimes in the question it is directly given that 130 kilojoule of work is done without mentioning that per unit kg term. Okay, so in that case some information related to mass would have been given also, and you have to put the value very carefully. If you are putting all the values in kilojoule per kilogram, this has to be in kilojoule per kilogram. Okay, so when you solve it, you will get u2 minus u1, u2 minus u1, this will be 18.136. okay, you're getting this as positive, 18.136 kilojoule per kilogram. Yeah. So this is your answer. Okay, so this is how you approach a question with the steady flow energy equation. Okay, this is how you solve it. Okay, let's take on some more questions from steady flow energy equation. Okay, try to do this question yourself. Okay, air as an ideal gas, air as an ideal gas flows at steady state. See, this term is given, steady state, this is the keyword. Okay, through the compressor. Okay, so air as an ideal gas is flowing at steady state through the compressor. That means it is flowing through a control volume. Okay, at steady state. So we can apply steady flow energy equation. Okay, through the compressor and heat exchanger as shown in figure. Okay, data for the flow streams are shown on the figure. Okay, this data is given. So neglecting the kinetic energy and potential energy effects and heat loss to the surroundings. So you have to neglect the kinetic energy and potential energy effects. Great. And heat loss to the surroundings. Okay, so Q is also 0, Q dot is also 0. The compressor power and the mass flow rate of cooling water are respectively. Okay, so this air is coming from this side in the compressor, it's going out from here, and then this hot air is actually cooled by this water in a heat exchanger. Okay, so that means T3 will be less than T2 because this air will be losing heat and this water will be gaining heat. Okay, and we have to find the mass flow rate of cooling water. The data is given to us. Okay, so pressure T1, P1, T1 and the data at T2 is also given to us, and one more thing that is given to us is AV1. What is AV? What is area into velocity? That is discharge, which is represented by Q. Okay, so this is given to us, but this is given to us in meter cube per minute. Meter cube per minute. So be careful whenever you use this data, divide this by 60. Okay, you can do it at the start also. Okay, you can just 26.91 divided by 60. This will give you meter cube per second. Q. Okay, Q dot. Yeah, we are representing heat loss by Q dot, so let's represent this by some other term. Let this be what? This be D, whatever you want. Okay, it's not D. It's difficult to write here. Yeah. So this is given to us. Okay. Now what we have to find? We have to find the compressor power, and the options are in kilowatt, okay, in kilowatt, not in kilojoule per kilogram. So that means you have to take mass flow rate into account. Okay, so let's apply the steady flow energy equation on this compressor by taking it as a control volume. Okay, so steady flow energy equation by taking this compressor as control volume. So what we can write, that is m dot h1 plus v1 square by 2 plus gz1, okay, and this is q dot is equal to m dot h2 plus v2 square by 2 plus gz2 plus w dot, that is power. Okay, so now it has been given that you have to neglect the kinetic energy and potential energy effects, so this gets cancelled out, and potential energy effects, so this also gets cancelled out. Great. And it has also been given that neglect the heat loss to the surroundings, so that means becomes 0. So what is left? This is m dot h1 minus m dot h2 is equal to w dot. So that means m dot h1 minus h2 is equal to w dot, that is power inlet to the compressor. Okay, so what is h? H is cpt. Okay, so I'll take cp common, so m dot cp, this is t1 minus t2. Now tell me whether t1 and t2 are given to you. T1 is given to me 300 Kelvin and T2 is given to me 400 Kelvin. Okay, okay, nice. So this is 300 and this is 400. And what about Cp? Cp is given to me. Cp, it's 1.005 kilojoule per kilogram Kelvin. That is 1.005 into 10 to the power 3 joule per kilogram Kelvin into m dot. Directly m dot is not given to you, but discharge is given to you. Okay, AV. So can you let me know that m dot, let me change the color for finding m dot. So m dot is rho AV. Okay, basic formula. Yeah. What is rho? Rho is 1 by specific volume. Okay, so that implies m dot is AV by specific volume. Okay, now any information given about specific volume? No, but you have been given with the P1, you have been given with T1, and air is given to you. So that means its characteristic gas constant is also given to you. Okay, so can you find specific volume at the inlet condition? Yes. How? You can apply this PV is equal to RT. Okay, so put this here. So that implies this m dot becomes AV 1 upon this is RT by P, so RT T1 P1. Okay, what are the values? P1 is 96 kilopascal, 96 into 10 to the power 3 Pascal. T1 is 300 Kelvin. R is 0.287. Let me write it only. 0.287 into 10 to the power 3. Okay, SI units. This is what, 96 kilopascal into 10 to the power 3. Okay, and AV1 is what, 26.91, but this is in meter cube per minute, so that implies 26.91 by 60 meter cube per second. T1 is 300 Kelvin. You can find m dot. When you find m dot, its value will be 0.5 kilogram per second. 0.5 kilograms per second. Okay, do I have a, oh, I don't have the space. So this is 0.5 kilogram per second. Put this value here. Okay, put this value here. You will get the power will be equal to this will be minus 50.25 into 10 to the power 3 watt. That implies minus 50.25 kilowatt. Why this minus sign? Why this minus sign? Because power is input to the compressor, power is given to the compressor, okay. So this means that the work has been done on the air, okay. So that means our answer is correct, okay. So the option 50.25 kilowatt, okay. And next is what? Next is you have to find the mass flow rate of cooling water, okay, mass flow rate of cooling water. So I've told you that the heat lost by air will be heat gained by the water, okay. So I'll solve this part here only. Heat lost by air will be equal to heat gained by water. Heat lost by air will be m dot A Cpa and its temperature change, which is equal to T2 minus T3, okay. And heat gained by water will be what? M dot water, that is mass flow rate of water, Cp of water into its temperature change, that is Tb, Ta, this is in, okay. So Tb minus Ta. Now what is given to you? Tb is given to you and Ta is given to you, so that means this term is given to you. Cpw is also given to you, 4.187. Put it in joule per kilogram Kelvin, or you can put it in kilojoule per kilogram Kelvin here, because this into 10 to the power 3 will get cancelled out by this into 10 to the power 3, okay. So Cpa is also given to you, T2 is given to you, 400, and T3 is also, this term is also given to you. M dot A we have found out. What is left? M dot W. So that implies mass flow rate of water required is this comes out to be 0.4 kilogram per second. 0.4 kilogram per second, but the options are in kilogram per minute, okay. So divided by, multiply it by 60 and you will get the answer in kilogram per minute, that is 24 kilogram per minute. This is the option, okay. So this is the solution of this question, okay. So this is how you do steady flow energy equation questions, and the questions are pretty simple in nature, okay. They are not tough at all, okay. Let's move on to the next question. So this is from heat and work for closed system. Air is compressed adiabatically from P1 is equal to 1 bar, T1 is given 2, P2 is equal to 15 bar, and V2 is given, okay. So initial conditions, pressure and temperature is given to you, and final conditions, pressure and specific volume is given to you, okay. After this, air is cooled at constant volume, okay. So first the air is compressed adiabatically, and then after this process the air is cooled at constant volume to T3 300 Kelvin, okay. So finally only temperature of air is given, and at this temperature the specific heat remains constant, okay, at Cv is given to you, okay. Neglect the kinetic and potential energy effects, neglecting the kinetic and potential energy effects, assuming ideal gas behavior, the work for the first process and the heat transfer for the second process respectively are, okay. So the kinetic and potential energy effects has to be neglected, they have given us, so I can directly apply first law, which says for the closed system, which says that delta Q is equal to du plus dw, okay. And says that the work for the first process you have to find and the heat transfer for the second process, okay. So for the first process, when the air is compressed adiabatically, in an adiabatic process heat transfer is 0. So first process, this becomes 0, okay. So we have to find work done, that implies W is equal to minus of delta U, nice, that is minus of mCv delta T, delta U is mCv delta T, and delta T is what? T2 minus T1, okay. So work done is T2 minus T1 into m into C, and this with a negative sign, okay. So T1 is given to me, T1 is 300 Kelvin, okay, and Cv is also given to me, and m, what about this m? I don't need m because the options are in kilojoule per kilogram. Kilojoule per kilogram. So take this m here. That is W by m. That means kilojoule per kilogram is equal to minus CV T2 minus 300. I am not given with this T2 value. T2 value, okay. I have to find this T2 value. If I get this value, I will be getting this work done per unit kg for the first process. So what other data is given to me? P2 is given, V2 is given, air is given. You can find out T2. Simple ideal gas equation. So this is P2, specific volume V2 is equal to R T2. Okay. So P2 is 15 bar, that is 15 to 10 to the power 5. Oh, yeah. 15 to 10 to the power 5 Pascal into specific volume is 0.1227 is equal to R, that is 0.287 into 10 to the power 3 and into T2. Okay. Solve it. You will get T2 is equal to what? T2 is 641.3. 641.3 Kelvin. This will be T2. Now what you have to do? Put this T2 here and put the value of CV. You will get the answer, and it will be the value will be equal to minus of what? Minus what is the answer? Minus 245.05. Take care of the units while putting the value. 245.05 kilojoule per kilogram. This will be the answer for the work input in the first process. Okay, see, we are getting the answer with a negative sign, and it is said that air is compressed. That means the work is done on the air, that is work is done on the system. Okay, and that means it should come with a negative sign. Great. Now for the second process, what is the second process? Isochoric. Okay, so Q is equal to delta U plus W. Isochoric, in isochoric process for a closed system, W becomes 0, PdV dV is 0, so W is 0. So Q is delta U in this case. Okay, now delta U is what? mCV delta T, and we have to find the answer in kilojoule per kilogram. So take this Q, so take this M in the denominator here. Okay, so this becomes small q is equal to CV delta T, and delta T is equal to T3 minus T2. Okay, so this becomes CV T3 minus T2. T3 is 300 Kelvin, T2 you have found out, that is this will be minus CV 341.3. is it 3 or yeah, it's 3. So you see that this is small w. Okay, so q is equal to the same value, that is minus 245.05 kilojoule per kilogram. Okay. So the heat transfer in the second process is also the same. So the option will be what? Option will be C. Okay. So next question is again from the heat and work for closed system. That's a topic, and this type of question you must have seen in many exams. The spring is connected and air is heated and the spring moves, and you have to find the what will be the work done by the air. Okay, you must have seen these type of questions in many examinations. So let me tell you how to approach these questions. Okay. So warm air is contained in a piston cylinder assembly oriented horizontally as shown in the figure. Okay. The air cools slowly from an initial volume of 0.003 meter cube to final volume of 0.002 meter cube. Okay. So the initial volume was 0.003 meter cube and the final volume was 0.002 meter cube. So this air cools down, and this piston, first of all this piston was suppose here, and then this piston moves downwards. Okay, Okay. So during the process, the spring exerts a force that varies linearly from an initial value of 900 Newton to a final value of 0. This is a very important line, that the spring exerts a force that varies linearly from an initial value, linearly. Okay. The atmospheric pressure is 100 kilopascal and the area of the piston face is given to you. Friction between the piston and the cylinder walls can be neglected. For the air, what will be the work done? Okay, so this is cooled, this is moving downwards. Okay, so if you draw the FBD of piston, this gas will be exerting a force, let it be P gas, okay, in this direction, and there will be pressure, atmospheric pressure, that will be exerting a force on this piston, and there will be a spring force also acting on the piston. So this can be written as P spring. This is pressure exerted by the spring, which is equal to F spring by area of the piston. F spring and the area on which it is acting, and here that area is area of piston. Okay, so this is the FBD of the piston. Okay, so it says that it exerts a force that varies linearly from an initial value of 900 Newton to final value of 0. Okay, so that means I can find out gas pressure by these values. Okay, why do I need this gas pressure? Let me tell you. Because these are the questions which I can directly solve by what? By this graphical method. Okay, so it says that the initial volume was 0.003 meter cube and final volume was 0.002 meter cube. Okay, and there was some pressure inside the air initially, and there is some pressure inside the air after it has reached this volume. Okay, what if I tell you this can be plotted linearly on PV graph like this? Because first of all the volume was 0.003 meter cube. This volume is in meter cube, and we'll take this pressure in kilopascal or pascal. We'll see that, and the final is 0.002. Okay, okay, and this can be plotted linearly. Okay, this is gas pressure. Okay, PG. Yeah, how? See, from this FBD, PG is equal to P ATM plus PS, that is P spring. So PG is equal to P ATM plus P spring, that is PS. Okay, now P ATM is constant, this is constant, let it be C, plus P spring. What is P spring? Pressure exerted by spring on the piston, that is force exerted by spring upon area. Okay, so that is force spring by area. Now tell me, what is this force exerted by spring? This is Kx. Okay, I'm just taking it Kx, not minus Kx, nothing. Okay, just to show you that this is a straight line. You can adjust the sign yourself. So this is Kx by A. Okay, so this K by A is also constant. Can I say this becomes an a straight line equation? Okay, because volume is a function of area into x, that is the piston, the distance by which the piston has moved. Okay, volume is Ax. So this is how you get this straight line. This is how I can plot the variation of gas pressure with volume. Okay, with volume as a straight line. Okay, because volume is also area into x. Okay, so this is x by which the piston has moved. And you also know that the area under the PV graph will give me work done directly. Okay, so V2 and V1 I know. Can I find P2 and P1? Yes, I can find out because the data is given to me, and this Pg1 is equal to P-atm plus PS1. Okay, atmospheric pressure is constant, that is 100 kilopascal. I'll be finding the pressure in kilopascal only. Okay, plus PS1. PS1 is okay, let me not confuse you. We try to solve all the questions in SI units, and also this is 900 Newton given. Okay, and not the value in kilonewton. So this is 100 into 10 to the power 3 plus PS1. PS is what? During the spring, during the process, the spring exerts a force that varies linearly from an initial value of 900 to a final value of 0. So that is F upon area. Area is 0.018. So whatever value you get, that will be Pg1, and that will be what? This is coming out to be 450, no sorry, 150 kilopascal. Okay, so that implies this is 150, and this is 150. This is in kilopascal. Okay, then okay, what will be P2? Again from the FBD, this F spring is now 0, so Pg becomes equal to P-atm, that is Pg2 is 100 kilopascal only. Okay, now you know every value. Find the area under this curve, which is a trapezium. Okay, and the work done will be area of the trapezium, which is half into sum of parallel sides into height. So half into sum of parallel sides, this is parallel side, this is 100 kilopascal, this is 150 kilopascal, so that implies 100 plus 150 into 10 to the power 3 into height, this is height, that is 0.003 minus 0.002, that is 0.001. Okay, let me write it more clearly, into 0.001. This is what this is, area into x. Okay, so when you solve this, you will get the answer in joules, but we have into 10 to the power 3, that means I can write the answer in kilojoules, and that will be 125. Oh, it's getting out, it's coming out in joules only, so that I mean we are getting the answer in joules, or 0.125 kilojoule or 125 joules. 125 joules, or you have to fill the answer in. Okay, oh, the options are given, so 125 joule. This is the answer. So this is how you approach a question. Okay, in case of a linear spring, okay, when the force is varying linearly, you can apply this method, and also the atmospheric pressure is constant. Okay, this is how you get this straight line equation, and you can solve all these type of questions by this method. Okay, no need to go for that long method, that PdV, integration of PdV, in which you actually have to find the equation and put the value of P in terms of V, and that's a long method. Okay, so just draw FBD, find the initial and final gas pressures, and find the initial volume and final volume of the piston, and and just find the area under the graph and solve the question. Next one. Oh, I had more space. Okay, so a system containing air undergoes a change of state from P1 V1 to P2 V2, whose values are given. The process undergone by the system is, okay, so the options are given. Isochoric, that is constant volume, V1 and V2 are not constant. This 0.8287 meter cube per kg is 1.435. Isobaric pressure is also not constant, that is 0.5 megapascal, and the final is 0.1 megapascal. Next is isothermal and isentropic. Okay, so we have to check that P1 V1 raised to the power n is equal to P2 V2 raised to the power n. If n is equal to 1, that means this is what, isothermal process, and if n comes out to be 1.4, in case of air we take gamma is equal to 1.4, so that implies if n comes equal to 1.4, this process is isentropic. Okay, yeah, so solve it. So this is 0.5 into 10 to the power 6, because it's in megapascal, it will get cancelled out only, but we make it a habit to write the units, write all the data in SI units. Okay, so this is 0.287 raised to the power n is equal to P2 is what? P2 is 0.1 into 10 to the power 6 into 1.435 raised to the power n. Okay, this gets cancelled out, this is 5, and when you solve this you will get, when you divide 1.435 by 0.287, this will be 5 raised to the power n, and you will see which gives me n is equal to 1. So that means it is a case of isothermal process. Okay, so C is the answer. Okay, next question. Next is, at a given point in the superheated vapor region, on a temperature entropy diagram, this is a general thermodynamics question. Okay, this was not from first law or this topic. Temperature entropy diagram, the slope of the constant pressure line as compared to the slope of the constant volume line is. This is a question directly from your theory portion. Okay, so slope of this graph will be dt by ds, and at constant volume, this is from thermodynamic relations. Okay, this question is from thermodynamic relations. You study it at a later stage in thermodynamics. When you solve those thermodynamic relations, you get dt by ds is equal to T by Cv when the volume is constant. Okay, and the slope in case of constant pressure is T by Cp. Okay, so from a point, which graph is having more slope, 1 or 2, will show how. So Cp and Cv, out of Cp and Cv, which has a greater value, that is Cp is greater than Cv. So that implies, if Cp is greater than Cv, that implies this value will be lesser than this value. So dt by ds at constant pressure should have lesser value than dt by ds at a constant volume. So we get the answer that the slope of the constant pressure line as compared to the slope of the constant volume line on this temperature entropy diagram is lesser. Okay, so that implies this is what, this is V is equal to constant, and this is what, P is equal to constant. I hope you know how to see the slope of the graph. Okay, so I'll tell you a very basic method to check if you don't know. So if you release a drop of water, just imagine this. Okay, so if you release a drop of water on curve 1 and on curve 2, the drop of water will travel faster, so that means it will have a, that means that curve 2 has more slope. Okay, just a very basic method to check slope if you don't know. So yeah, so this was all in this video, and I've solved, I guess, important questions in this video covering steady flow energy equation and that question related to springs, work done by the gas in a piston cylinder arrangement when the piston is connected to a spring. Okay, so those were important questions. I'll meet you in the next video with some more questions from these topics, and we'll learn some more concepts. Okay. And also I'll be taking some questions from that topic when the tank is connected by a pipeline and it's having some enthalpy, and you find out the final temperature of the gas in the tank. I'll be dealing with all those questions, and I'll be showing you how to solve them. Okay, so thank you.